The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I'll respond as soon as I can. All right, so today we're going to wrap up the chapter and wrap up the course. We're going to look at a little bit from 11.6, some from 11.7, and then tonight you'll have 11.6, 11.7 in the chapter review to do. Tomorrow we'll review. Friday you'll take your chapter 11 test. Monday and Tuesday during regular meeting time, we'll review for the final, which is on Wednesday. Okay, so what we're going to do right now is we're going to take a look at problem number. Come on, here we go. From 11.5, problem number 35, which is over on the left side of the screen. It says, Kuwait, located at the head of the Persian Gulf, has some of the greatest population growth rates in the world. Bulgaria in Southeastern Europe has one of the smallest. Use an exponential growth decay model to complete the table. Round your answers to the nearest integer. All right, so we're going to use A equals P e to the RT power. So let's deal with Kuwait first of all. So for Kuwait, let's see here. Kuwait, what have we got? Well, the beginning population is 2,789,132. The growth rate is 3.501%, which would be 0.03501. Be careful that you get the conversion correct. And the time from 2010 to 2025 is 15 years. So what have we got? We've got A equals 2,789,132 times e to the power 0.03501 times 15. Okay, so on the calculator, we've got 2,789,132 times e to the 0.03501 times 15, close it up, and I get A equals 471,562.0.159, and it says to round to the nearest integer, which would be there, so 471,562.0. So the new population, 4,715,620. All righty, and then next we have Bulgaria. Let's see here a little bit, and Bulgaria, the population is 7,148,007. Somehow I activated the wrong button. Sorry about that. Give me just a minute to get my act back together here. I do so love switching screens. Let's see here. No, that's the one I want. There we go. Okay. And let's see here. I think it's erased everything I had. Okay. Anyway, so we've got Bulgaria. The beginning. Oh, now we're in red. Hang on. Sorry about this. Yeah, reset everything. All that from pushing the wrong button. Oh, well. Okay. The population, P, is 7,148,785. The annual growth rate is negative 0.768%, which would be negative, let's see, 0.00768. 2, yeah. And the time is also 15 years. So we've got A equals 7,148,785 times e to the negative 0.00768 times 15. So let's see what happens when we put all of that into the calculator. 7,148,785, that's a 5. E to the negative 0.00768 times 15, and I get 637,091.0.61. Rounding to the nearest whole integer, this 6 would round up, so 6,370,911 would be the new population. Okay, so now we are going to go back to the other screen. And so give me a minute here to get things reset. Now you should be seeing my whiteboard screen. Could somebody just verify that that is what you're seeing?
Yeah.
It's up.
Okay, great. Thank you so much. All right, now we're going to go back to a problem that I introduced several days ago when I said that, let's see here, 2 cubed was 8, 2 to the 4th power was 16, and 2 to the x power, I believe I used 11. And I said, well, to solve for x, we could take 2 to the x power equals 11, and we could change it into a logarithmic equation, which would be log base 2 of 11 equals x. Or in fact, I'm going to rewrite it this way, x equals log base 2 of 11. The problem is, most of us, our calculators don't have a log base 2 button. Some of you might actually have a calculator that has a little box there and a little box there, where you can use that to not have to use this next formula. But for the rest of us, we're going to use what is called the change of base formula. And this is the only thing we're going to look at out of section 11.6, the change of base formula. And this is what it says. It says log, maybe, log base b of x equals log base a of x over log base a of b. Now, again, keep in mind restrictions, the base, what has to be positive and not equal to 1. But since our calculators have log base 10 and log base e, what we should do is choose this as either 10 or e. So for this given problem, I could rewrite this as log base 10 of 11 over log base 10 of 2, which of course on my calculator, I would just enter it like this. In other words, I wouldn't have to write the base 10, or I could write it as natural log of 11, that is log base e, over natural log of 2, that is log base e of 2. And in both cases, I'm going to get the same answer. So on my calculator, let's see, log base 10 of 11 divided by log base 10 of 2, and I get 3.459431619. And then I clear it and I go natural log of 11 divided by natural log of 2, and I get the exact same answer. Now, be careful when you enter this or this into your calculator. For instance, log of 11 divided by log of 2. A left-hand parenthesis shows up when you push log base 10. Make sure you close that up before you put the division bar, okay? Otherwise, it's going to think you want that, which gives you a completely different answer. If you could even read that, let's see here. divided by log of 2. Okay. Now, so what this is saying is that this, and again, that number is rounded, but this is the number that would go here. So 2 raised to the 3.459431619, blah, 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 would be approximately 11. And I say approximately because this is rounded off. Okay. So that's the change of base formula. Let's apply that to some examples. So here we go. We've got, it says, use the change of base formula to find each logarithm to 4 decimal places. So log base 3 of 7. Well, that would be common log or log base 10 of 7 over common log or log base 10 of 3. So on my calculator, log of 7, close it up, divided by log of 3, close it up, and I get 1.77124. It said to 4 decimal places, the 4 would round down, so I'd get that. Or I could do this and get the same answer. Natural log of 7, close it up, divided by natural log of 3. Okay, now understand this. Log of 7 is not equal to natural log of 7. Log of 3 is not equal to natural log of 3, but the ratio of these two is equal to the ratio of those two. And make sure you use the same base. Don't do this. Don't do log of 7 over natural log of 3. Okay, the bases have to be the same. All right, another example, log base 1/2 of 6. So this would be the natural log of 6 over the natural log of 1/2. Natural log of 6, close it up, divided by natural log of 1/2. And that's negative 2.58496, etc. Let's see here. This is 4 places. The 6 rounds up. So 850. Okay. Any questions about that? All righty then. We're going to go on to section 11. That is 11.7. Excuse me. Okay. And let's take a look at some problems. This says solve each equation. And we have 6 to the x minus 2 power equals 36. Recall from a previous section that if we could rewrite this so that the bases were the same, we can then say that the exponents are equal. So by taking 36 and writing it as 6 squared, now they both sides have a base of 6, the exponents are equal. And then we can go on and solve this equation, x equals 4. Let's check our work. And it checks. Any questions about that problem? Okay, let's take a look at another example. 5 to the 4x power equals 1 over 125. Well, I can take 125 and write it as 5 cubed. I can take 1 over 5 cubed and write it as 5 to the negative 3 power up on top. So now I have 5 to a power equals 5 to another power. So the powers are equal because the bases are equal. Solving for x, I get x equals negative 3/4. Let's check our work. Let's see here. 4 times negative 3/4 would be negative 3. And this would be 1 over 5 cubed, which would be 1 over 125. And so it checks. All right. Well, this is all fine and dandy. On these last two examples, we were able to match the bases. But what if I have something like this? 4 to the x power equals 5. I have no idea how to take 5 and write it as 4 to some power, or to take 4 to the x and write it as 5 to some power. But I could do this. I could change this into a logarithmic equation. Okay, so this would be log base 4 of 5 equals x. Now, the reason I went equals x back to the left instead of to the right is because now I'm going to use the change of base formula to rewrite that expression. And there I can go to my answer. So I've got log base 10 of 5, close it up, divided by log base 10 of 4, close it up. 1.160964, et cetera, and it says round to 4 decimal places, the 6 would round up, so we're going to get that is our answer. So what did I do? I changed the exponential equation to a logarithmic equation and then used the change of base formula. Any questions about that problem? All right, let's look at another example of that. I have 13 to the x minus 1 power equals 2. Again, I can't see how to get those with the same base, so I'm going to rewrite this as log base 13 of 2 equals, leave myself more room here. Log base 13 of 2 equals what? X minus 1. Well, I'm going to have to add 1 to both sides. So x equals log base 13 of 2 plus 1. And that 1 is not inside the log. Okay. In fact, maybe it would be better to write it. Let's see here. To put the plus 1 in front. It's the same value, but then maybe you're less tempted to get that 1 sucked into that log. Okay, so now this is 1 plus log of 2 over log of 13. And let's see, 1 plus log of 2, close it up, divided by log of 13, using base 10 in both cases. And I get 1.270238. 4 places, the 3 would round down, 1.2702. Any questions about that problem? All right. Now, here's some other examples, but it involves a base of e. Solve each equation, give the exact solution, and an approximation to 4 decimal places. So e to the 2.9x power equals 4.5. I have no idea how to make 4.5 e to some power. So I'm going to rewrite this as log base e of 4.5 equals 2.9x. But isn't log base e natural log? So I've got that. Divide both sides by 2.9. So x equals the natural log of 4.5 divided by 2.9. So there's your exact answer. And let's see, I've got the natural log of 4.5, close it up, divided by 2.9. And I get 0.51864. Again, it said round to 4 decimal places, so that is going to round down 0.5186. Any questions there? All right, let's take a look at this problem. It says solve each equation. Log of 2x equals 4. Keep in mind that there is an implied 10 because it just says log. I could take this logarithmic equation and rewrite it as an exponential equation. Solving for x, x equals, let's see, 10 to the fourth power divided by 2, which would be 5,000. Any questions about that? Okay, here's another one. Log base 3 of x minus 3 equals 2. Changing this to an exponential equation, 3 squared equals x minus 3. See, I don't really need the parentheses there now, do I? So 9 equals x minus 3. Add 3 to both sides. X equals 12. Let's see. Let's take a look at another one of those. Log of 1/8 x equals -2. So again, the base is 10. So 10 to the -2 power equals 1/8 x. Okay. 1 over 10 squared equals 1/8 x. 1 over 100 equals 1/8 x. Multiply both sides by 8. 8 over 100 equals x. We could divide the top and the bottom by 4 and have 2/25. Yeah, let's see here. Or as a decimal, what? 0.08 if we used our calculator. All right, any questions there? Let's say we've got the following. Log of 3 minus 2x equals log of x plus 24. Because like exponential functions, logarithmic functions are one-to-one functions. If we have log base 10 of something equals log base 10 of something else, the something is equal to the something else. Now, the process of getting there, of removing the logs and everything, that's something that we're not going to cover this quarter. We'll use that topic in Math 141 for those of you that go on to that. But now, solving this, I'll subtract x from both sides. Subtract 3 from both sides. Divide both sides by -3. X equals -7. Let's check our work. Log of 3 minus 2 times -7 equals log of -7 plus 24. Log of what? 3 plus 14 would be 17 equals log of -7 plus 24, 17. Log of 17 equals log of 17. So it checks. Okay. Let's see here. What are we doing for time? Yeah. All right. Now, so far, we have looked at the following formulas, and you're allowed a formula chart or paper or whatever for your test. And at the end of class, I'll go through again all the formulas you can have on it. But what have we got so far? We've got this one, A equals P times 1 plus R over K to the KT power. Compound interest, where it's compounded not continuously. A equals P e to the RT, where it is compounded continuously, whether it's involving money or a population. And then we had what? The time equals the natural log of 2 over the growth rate was a shortcut we could use. Okay. And let's see here. Give me a second to get organized on this new stuff. Aha.
What was the last one again?
This one right here.
Yeah.
That's where we looked at a couple of problems yesterday where like you're wanting to double your money or double the population. If you know that you want to double it and you know the growth rate, rather than plugging it all into this and going through all the work, you can just jump straight to this formula. But that's involved when you're doubling something. If it's got continuous growth, then you're doubling. Does that make sense?
Yeah, thank you.
Okay. All right. Let's see here. All right, now let's take a look at this problem. It says tritium decay, or tritium, I'm not sure. The half-life of tritium is 12.4 years. How long will it take for 25% of the sample of tritium or tritium to decompose? Half-life. Well, let's talk about the idea of half-life, okay? And I'm just going to use a bizarre example just because I like to. Let's say that there's a refrigerator that has 128 Snickers bars in it. Okay. And 1 week later, I go back and there's 64. I'm going to put SB for Snickers bars. Okay. And then 1 week later, there's 32. And then 1 week later, there's 16. And then 1 week later, there's 8. And so every time a week goes by, we lose half of what was there at the beginning of that time. Okay. Now Snickers bars aren't alive, hopefully, but let's say we've got some kind of radioactive substance or something like that where it's going to decay. Okay. The half-life is how long does it take for the beginning amount to cut in half? Okay. 2 half-lives do not a whole life make, or no life for that matter, because you lose half of what you had at the beginning of that ending period. So in other words, I don't lose 64 and then 64 and I'm down to 0. You lose half of what you start with at the beginning of the week. So in this case, the half-life is 1 week. Okay, now the formula for half-life is this. A equals A sub 0 times 2 to the negative t over h power. Okay, let me write that a little better. Negative t over h power. A sub 0, or A naught as it is often called, is the beginning amount. A, over on the left side of the equation, is the ending amount. T is the time and h is the half-life. Okay, now the base is 2, so you would think things are doubling. But if you consider this, isn't that the same thing as that? Where, in which case, if the base was a half, you would be getting half of what you had. But this author chooses to write it this way. So that's what we'll do. Okay, now let's go back and look at our problem. Tritium decay, the half-life of tritium. So H equals 12.4 years. That was given in the problem. How long will it take? So that's time for 25% of a sample of tritium to decompose. All right, now they don't tell us the beginning amount. So the beginning amount is A sub 0 or A naught, okay? The ending amount, well, let's see. If 25% is going to decompose, how much do we have left? We have 75%. 75% of what? The beginning amount. So the beginning amount is A sub 0. The ending amount is 0.75 A sub 0. That is 75% of the beginning amount, because we're losing, it says 25% decomposes. All right. So we really don't even know how much there is. We don't need to though, because now substituting all these numbers into the formula, A is 0.75 A sub 0 equals A sub 0 times 2 to the negative t over 12.4 years. Okay. Any questions so far? My next move is to divide both sides by A sub 0. So now I get 0.75 equals 2 to the negative t over 12.4 power. I now have an exponential equation in the correct form to convert it into a logarithmic equation. Why do I want to do that? Because my unknown t is part of the exponent. So this becomes log base 2 of 0.75 equals negative t over 12.4. Okay. Now, to isolate t, I'll multiply both sides. Well, if I multiplied by 12.4, I'd get rid of the denominator, but I still have a negative in the numerator. So why don't we get rid of it all at once by multiplying both sides by negative 12.4. On the right side, negative times negative is positive. The 12.4 is reduced out, and I have t. On the left side, I have negative 12.4 log base 2 of 0.75. So I've solved for t. There's the exact answer. Now let's get an approximate answer. Okay, I'm going to rewrite this equation. T equals negative 12.4 log base 2 of 0.75. But I'm going to use the change of base formula. So I get negative 12.4. Let's use natural log this time. Natural log of 0.75 divided by the natural log of 2. That's all going to go into my calculator. So negative 12.4 natural log of 0.75, close it up, with parentheses, divided by the natural log of 2, close it up, and I get 5.14646499111, and they rounded to the nearest tenth of a year, which would be right there. So t is 5.1 years. Now, I believe in WebAssign, it will tell you what to round to, okay? So it'll say round to the nearest tenth or hundredth or thousandth or integer or whatever. Do you have any questions about what happened here? Okay, let's take a look at another example. Radioactive decay. In 2 years, 20% of a radioactive element decays. Find its half-life. So again, we're going to use the half-life formula. All right, let's see, in 2 years. So the time is 2 years. 20% of a radioactive element decays. Find the half-life. The half-life is the unknown. So let's see. Again, we don't know how much we're starting with. So we're starting with a sub 0 or a naught. It says in 2 years, 20% of a radioactive element decays. So if 20% goes away, we still have 80% of the starting amount. And I could write 0.80 or just 0.8, either way. Okay. So what have I got? A, which is 0.8 a sub 0 equals a sub 0 times 2 to the negative 2 over h power. Any questions at this point? If I'm going too fast, let me know. I can slow down. We're going to divide both sides by a sub 0. So 0.8 equals 2 to the negative 2 over h power. I'm going to change that to a logarithmic equation. Log base 2 of 0.8 equals negative 2 over h. Well, in the last problem, we were trying to solve for t, which was in the numerator, and that made things much nicer. Now it's in the denominator, so things are going to be a little trickier. We're going to multiply both sides by h. So I'm going to get h log base 2 of 0.8 equals negative 2. But then I'm going to divide both sides by log base 2 of 0.8. So I have h equals negative 2 over the log base 2 of 0.8. Okay, so there's an exact answer. But to put that in the calculator, I'm going to use the change of base formula. I'll use base 10 this time. So I've got that over that. And I'm going to quantify that. So H equals, in my calculator, -2 divided by parentheses, log base 10 of 0.8, close that up, divided by log base 10 of 2, close that up, close up the whole thing. So basically, I've got a set of parentheses here and here, as well as that outer set. And I get 6.212567, etc. And let's see, it said in years, so this would be about 6.2 years. Any questions on the algebra there? Okay. Let's see here. Take a look at this one. Carbon-14 dating. A bone fragment analyzed by archaeologists contains 60% of the carbon-14 that is assumed to have had initially. How old is it? So carbon-14, this has to do again with half-life. So A equals A naught 2 to the negative T over H power. A bone fragment analyzed by archaeologists contains 60% of the carbon-14 that is assumed to have initially. How old is it? So time is our unknown. The half-life isn't given in the problem, but in the reading, it says that the half-life of carbon-14 is 5,700 years. Okay. Again, what's the ending amount? What's the beginning amount? We don't know the beginning amount. Now, in the last two problems, it said, let's see, 25% decomposes, 20% decays. This one says a bone fragment contains 60% of carbon-14. So they're not telling us how much is lost, they're telling us how much is left. So the ending amount is 60% of the beginning amount. We don't take 60 from 100 and get 40. It lost 40%. So we've got to read carefully. It's not meant, I'm not trying to trick you. I'm saying you got to read it carefully. Sometimes it tells you how much is lost. Sometimes it tells you how much is still there. All right. So now we've got 0.6 a sub 0 equals a sub 0 times 2 to the negative T over 5,700 years. We're going to divide both sides by a sub 0. 0.6 equals 2 to the negative T over 5,700 years. I'm going to change this to log base 2 of 0.6 equals negative T over 5,700. Just like I believe it was the first example I did, we can multiply by negative 5,700. And that'll get rid of the 5,700 and the negative. So now I've got T equals negative 5,700 log base 2 of 0.6, which is negative 5,700. Change of base, I'll go back to natural log of 0.6 over natural log of 2. Negative 5,700, natural log of 0.6, close it up, divided by natural log of 2, close it up. And I get 4200.7038. And so they say about 4,200 years. Be careful when you're pushing buttons that you push the right one, you push L in and L in, or LOG and LOG, or whatever. Don't get your buttons mixed up. Okay. Okay, let's see here. Just a second. The author has a different variation of this formula, and it looks like this. Oh, it's, hang on, did that wrong. Like this. That's P. P equals P sub 0 e to the KT power. It's really just a variation on this same formula. here's your beginning population, here's your ending population, this is your growth rate, this is your growth rate, okay? So I'm not gonna burden you with one more formula there because they both accomplish the same thing. So we're gonna do a couple more problems, but what have we got now in terms of formulas? We've got this. We've got, oh, hang on. That. We've got that. And that. I think that's it. So compound interest, not continuously, growth rate continuously, doubling time, knowing that you have the growth rate, and then half-life formula, okay? So you can have those 4 formulas on a card for your test if you want. Now, this problem says compound interest. If $500 is deposited in an account paying 8.5% annual interest, compounded semi-annually, how long will it take for the account to increase to $800? The key word in that whole thing is semi-annually. If it had said continuous, we'd use A equals PE to the RT, but it says semi-annually. So we're going to use this formula. Okay, $500 is deposited in the account paying 8.5% annually, compounded semi-annually, so that's twice. How long will it take for the account to increase to $800? So time is the unknown. Isn't that true? Okay, so what have we got? We've got $800 equals $500 times 1 plus 0.085 over 2 raised to the 2t power. Okay. Well, let's see. Let's take the insides right here and let's simplify that. Okay. So if I take 0.085 divided by 2, so 0.085 divided by 2, I get 0.0425. And then 1 plus that would be 1.0425. So that gives me $800 equals $500 times 1.0425 raised to the 2t power. So far, so good. Now, there's a problem here. I can't change this in its current form into a logarithmic equation because there's this number out in front of the base. So what am I going to do? Well, I'm going to divide both sides by that $500. On the left side, let's see, a 0 goes, a 0 goes, a dollar sign goes, and I've got 8/5 equals 1.0425 to the 2t power. Now it's in the form of a number equals a base to a power. I can change it into a logarithm, okay? Logarithmic equation. I'm running out of room, so I'm going to recopy this, this on the next page. So 8/5 equals 1.0425, 1.0425 to the 2t power, right? Now, 8/5 comes out exactly as 1.6. If it didn't, if I divided it and I got some crazy repeating or just continuous decimal, don't round it off, okay? But this one comes out nice. I'm just going to leave it as 8/5. So now what have I got? I've got log base 1.0425 of 8/5 equals 2t. I'm trying to solve for t. Well, I could divide both sides by 2. then I'd have this whole thing divided by 2. There's a nicer way to deal with that. What if I multiply both sides by 1/2? On the right side, 2 times t times 1/2 is t. So I've got t equals 1/2 log base 1.0425 of 8/5. So now t equals 1/2 times, I'm going to use, we'll use natural log again. Natural log of 8/5 over natural log of 1.0425. And now go to the calculator. And let's see here. We've got 1/2. So 1/2 times, let's see here. 1/2 times the natural log of 8/5, close it up, divided by the natural log of 1.0425, close it up. And I get 5.6461 etc. And let's see, what did they do? They said about 5.6 years. Okay. Any questions about that? All righty. So you've got a few problems from 11.6 to practice the change of base formula, which then you'll use in problems from 11.7. If you can't get the chapter review done, because tomorrow we're going to review for the test on Friday. I will be back this afternoon at 1:15 with an office hours. If you have any questions, anyway, I'm going to stop the recording.